Hello everyone. Today we will begin our study with one of the most common structural elements, beams. In these videos, we are going to answer two questions. What is a statically determinate beam and how to analyze it? So what is the beam? So beams is a rubberly supported structural member capable of carrying loads. So it can be a point load. It can be distributed load or concentrated moment. That are the forces or moments having their vector perpendicular to its longitudinal axis. Such a member is called a beam because the loss causes it to bend like this. So as we can see, all loss act in the same length, and if all deflections occur in the plane, then we refer to that plane as a plane of bending. Beams are usually described by the manner in which they are supported. Now, before analyzing beam, let's have a quick look on the three most common support types. Roller support. At the roller support, beams is free to move along the support. It can rotate about the support also. See the photos of the wrist structures. Let's check out horizontal roller support, vertical roller support, and inclined roller support. For the horizontal roller support, there is one reaction, that is force in the y directions. That is a similar way to vertical roller support and inclined roller support. There is one reaction associated with the roller support, that is the force in the direction perpendicular to the support surface. Beam support. Beam support can be called as hinge support. At the hinge end, the beam cannot move in any directions. However, it can rotate about the support. Consequently, a pin support is capable of developing a force reactions in both horizontal and vertical components, but it cannot develop a moment reaction. There are two reaction forces associated with the pin support, a force in the x direction and one in the y direction. And a fixed support, the beam end is not free to straighten or rotate. Hence, there are three reactions. A force in the x direction, a force in the y direction, and the bending moments about the z-axis. As we can see, a reaction force at the support is represented by a single arrow with a slash through it, while a moment restraint at the support is always a curved arrow with a slash. Now let's talk about the types of the beam in conjunction with the types of the supports discussed above. Consider a beam with a pin support at the one end and a roller support at the other end. It's called a simply supported beam or a single beam. Turn to the beams with a fixed at one end and free at another end. That is called as cantilever beams. At the fixed support, the beam can neither straighten nor rotate, whereas at the free end it may do both. Consequently, both force and moment reaction may exist at the fixed support. Overhand beams. This beam is simply supported at points A and P, that is, pin support at A and roller support at B, but it also rotates beyond the support B. The overhanging segment BC is similar to cantilever beam except that the beam axis may rotate at point P. Continuous beam. A beam that is supported at more than 2 points, or it may have multiple continuously spans. This beam is constrained by additional support or redundant supports. Now come to the next topic of beam analyzing. We are going to talk about the loss on beams. External loss applied to a beam may be either concentrated or distributed forces or moments. So let's start with concentrated loss. When the loss is applied over a very small area, it may be idealized as a concentrated loss or point loss. Examples are the loss P1 and P2 with units of kilonewtons act on a beam. The concentrated moments MA and MC with units of kilonewton meter acting at point A and C respectively. The beam is subjected to clockwise moment of 30 kilonewton meters at point A and counterclockwise moments of 10 kilonewton meter at point C. Turn to distributed loss. When the loss is spread along the axis of the beam, it is represented as distributed loss. Distributed loss are measured by their intensity, which is stressed in the units of force per units of distance. This is uniformly distributed loss or uniform loss, has constant intensity Q per unit distance. It is represented as so with its constant intensity 10 kilonewton per meter. This loss may be assumed as total loss acting at the center of gravity of the loadings. For example, the given loss may be replaced by a 40 kilonewton concentrated loss acting at a distance 2 meters from the last support. A uniformly varying loss has an intensity that changes with the distance along the axis. As you can see, the loss varies uniformly from C to D. Its intensity is 0 at C and 20 kilonewton per meter at D. Calculating the area of triangle gives us the total load. In this case, it equals 60 kilonewtons acting at the center of gravity of the load, which is 2 meters from this. A free body diagram is an essential part of a static analysis of beams. All forces acting on the beam need to be displayed on the FBD if a correct equilibrium solution is to be obtained. For example, the solution for reaction forces at A and B must begin with a rubber drawing of the FBD of the overall beams. So the FBD shows on applied and reactive forces. I will show you how to solve the reaction forces using the FBD in the next video. Equilibrium equations. Equilibrium equations help us to find external reaction forces and moments, which is a very important part of analyzing beam. At equilibrium, the beam will not be moving. Hence, the resultant force R and the resultant moment F of all forces and moments acting on the beams in equilibrium are both zero. It can be written in scalar forms using coordinate system in 2 dimensions as the sum of force in the x direction equals 0. The sum of forces in y directions equals 0. And the sum of moments about the z-axis equals 0. The sum of moments may be taken about any arbitrary point. If the number of unknown forces is equal to the number of independent equilibrium equations, it means those equations are sufficient to solve for all unknown reactions or internal forces in the body, and the problem is referred to as statically determinate. If the beam is constrained by additional supports, such as in continuous beams, it is statically indeterminate, and the solution is not possible using the laws of static equilibrium alone. We will discuss about this later in the next following videos. In the next videos, I will show you how to find support reactions in a beam and solve for internal forces at the arbitrary point along that beam using equilibrium equations and rubberly raw reef body diagrams. Give this video a thumbs up if you found this video valuable. Leave me a comment if you have any questions or concerns, and thanks for watching videos.